We've been able to solve for unknown side lengths and angles in right-angled triangles only so far. We're going to extend that now to any shaped triangle. We have a naming convention that we use. Now in that triangle there you can see that we've used capital letters to represent the points or the vertices of the triangle. The capital letters also refer to the measure of the angles as well in that triangle. More formally, if we want to refer to the actual angle itself, we should use the angle symbol. So we can use angle A to represent the angle at A, or more formally angle BAC. But we can also use the A, B and C to refer to the size of the angles. So when we add those three angles up, we get 180 degrees there. Lowercase letters are used to represent the side lengths, and you'll notice that the side length A is the side that's opposite the angle A, and the side length B is opposite the angle B, and the side length C is the side that's opposite the angle C. The sine rule states that the ratio of a side length to the sine of the opposite angle are equal in any triangle. We can flip that over the other way round and write it that way. And the first form is useful if we're trying to find an unknown side length, and the second form is useful if we are trying to find an unknown angle. So we use the sine rule when we have two angles and a side, or two sides and an angle. Let's have a look at a proof of the sine rule. We'll drop an altitude from C down to the side C, and then we can say that the length of that side H in the right angle triangle at the left there is B times the sine of A, and using the other side there we can say that it's A times the sine of B in the second right triangle there. So dividing that by sine A times sine B, we will get that relationship there. And that is, of course, the sine rule, and we can extend that by doing similar constructions with altitudes from A and another altitude from B, and then we'll get the relationship that will include C as well. There is an ambiguous case with the sine rule. If we know two side lengths, A and B, and we know an angle, but it's not the included angle, it's an angle at the end of one of those sides like that, then we can have two situations. We can have A as shown there, but we can also have A there as well. So we may end up with two different triangles. In this example, we have a triangle with a known side length of 45.7 centimeters with angles of 49 and 66 degrees on either end of that side. We want to find the size of the remaining angle and the length of the other two sides. So firstly, we depict the situation in a diagram. Known side length of 45.7 with angles of 49 and 66 on either end of that. We'll label the points on the vertices there, and then we'll also use that naming convention where the side length opposite the angle B is little b, and the side length opposite C is little c. So this side length that we know is side length A. We can easily find the unknown angle A by the fact that the three angles have to add up to 180 degrees. So we'll add up the two known angles, subtract that from 180 degrees to get A as 65 degrees. We can now use the sine rule to work out the unknown lengths B and C. Starting with B, we have B is what we're trying to find. We know the angle B, so we can use B over sine angle B is equal to, we know A, so we'll use A over sine of angle A, which we've now worked out. So putting all the values in that we know and multiplying up by sine of 49 degrees, we'll get that answer for B, which we can then calculate out on our calculator, making sure that our calculator is in degrees. Next we'll find the unknown side length C, and we'll substitute the values in that we know. We'll again use A and sine A rather than to use B that we've calculated here, because there were more calculations to obtain that answer, and we may have made a mistake through there. Again, we'll do that on our calculator to get our answer of 46.1 centimetres. We'll tackle the ambiguous case in this example. We have a triangle with one side of 12.1, another of 15.7, and a non-included angle of 42.5. We're asked for the length of the third side, which we'll label as C because it's opposite the angle C. Now, in order to find that length C, we need to know the angle C. To find the angle C, we need to find the angle B. And we'll use the known length of B, A, and the known angle to find the angle B using the sine rule. So we'll substitute all the values in that we know and then calculate it out on our calculator. Now we need the angle, so we'll have to use inverse sine here, and we will get 61.2 degrees as our answer. Now that angle is the angle shown in the first quadrant there, but there is another angle in the second quadrant that also has the same sign. That's given by that angle there, which is 180 minus that 61.2 degrees. So if we take that away from 180, we'll get our second answer, which is 118.8 degrees. We now have to use each of those angles separately to work out the unknown angle and side. So we can simply subtract the sum of those two known angles from 180 to get our angle of 76.3 degrees for C. We now can use the sine rule to find the unknown side length C, and we substitute all the values in now that we've got, including that angle C that we've just calculated, and we'll get 17.4 meters. That is, the base of that triangle there is 17.4 meters. Now when B is 118.8 degrees, then our triangle is no longer the same as what we had above. We have the ambiguous case, and so we have a new triangle that looks like that. Our angle is 118 there, 118.8 degrees for angle B. We can now find C as we did before by adding the two known angles and subtracting from 180. So our angle C this time is 18.7 degrees. We use that angle in conjunction with the sine rule to work out our unknown length C, which will be 5.75 meters. Notice that our answer here is a lot smaller than our previous answers, so we're happy that we've done our calculations correctly. The cosine rule states that that side A squared is equal to the square of the other two sides added together minus 2 times the product of those two sides times the cosine of the included angle A. So we can use the cosine rule if we know the two sides B and C and the angle A, and we can find the unknown side length A. We can also use the cosine rule if we know the three sides A, B and C and we are trying to find the unknown angle A. We can rewrite the cosine rule with either B or C as the subject, not just A. So for example, if it was side length C that we are trying to find, we can then say that C squared is equal to the square of the other two sides A and B minus 2 times the product of those two sides times the cosine of the included angle C, which is the angle that's opposite the side C. Let's now prove the cosine rule. We'll drop an altitude from B to a point that we'll label D. We have a triangle ABD, that's a right triangle, so we can express the side H as the hypotenuse C times the sine of the angle A. We'll label the side length in the base there as R, and we can express R as C cosine of A. We now have another triangle on the right there, that's BCD, that's also a right triangle, and we can use Pythagoras theorem in that triangle. So the hypotenuse squared is equal to one side squared plus the other side squared. This side here is B minus R. So now we'll replace the H with C sine A, we're squaring it, and the R we're going to replace with C cosine A. We now expand this bracket to get the first term squared, 2 times the first times the second there in the middle, and then we'll get the last term squared. We'll now simplify that by gathering up the c squared terms. We've got a sine squared and a cosine squared that are being multiplied by the c squared, and the other terms will leave by themselves. Now the sine squared plus cosine squared equals 1. So that leaves us with a b squared, a 1c squared, minus a 2bc cosine a, which is the cosine rule. In this example, we are trying to find the unknown length A in this triangle, and we know the two other sides there and the included angle, so we can use the cosine rule straight off in its original form, A squared equals. So we substitute for B and C and angle A, and then we calculate that out on our calculator. We'll get our A squared first and then take the square root of that to get 4.7. So we've seen that we can find unknown side lengths and angles in any shaped triangle, not just right angle triangles, and that the naming convention is that we use lowercase letters for the side lengths, uppercase letters for the vertices and the angles, and that the angle A is opposite side A, and so on. The sine rule was given as that, where we have the ratio of the side length to the sine of the angles, and the cosine rule was given as that.